All right. So I wanted to bring up your superhero paper. How many have actually read the instructions? I'll be honest, that's pathetic. How many know when the deadline is, the first deadline? Now, it's not to scare you because you got quite a ways. But that's my point is I'm holding you to those. There's 3 deadlines involved with the superhero paper. And know when those are so you get your ideas. I mean, if you want to write the paper the night before, that's fine, but it probably won't be as good. Just don't forget about it. I'd also like to address any questions or concerns you have it soon, because some people tend to start about now. And again, you can use any superhero power. It doesn't have to be concepts we've only covered so far or even are going to cover. As long as it's physics, you can do it. And I'm happy to approve that if you're worried. But do look that over in the next bit so we can just, if you got questions, we can discuss it in class so you guys know where you're headed before it's too late, because we don't want that to happen. It is a short paper. I'm not trying to just give you busy work. But any questions somebody has right now? Because a few of you read it. Did it make sense? There's a lot of info crammed in there. Good. All right. Well, you guys ready for chapter 6 then? Just curious. Who's read it? Hey, a few of you have. Good. You're going to get more out of this lecture than everybody else. That's good. So we're doing chapter 6 on momentum today and Friday. And then next week will be energy on chapter 7. And then chapter 10, for those of you getting ahead, we're doing the projectile motion part only. So you don't have, well, you can read the other, but I'm not testing you on it. So just the projectile motion part. Then we're going to skip to chapter 35 and have fun with special relativity, because I think it's cool and you guys will think it's weird. But you're prepared for it after all that stuff that we've covered with forces and motion, momentum and energy. And I bet all of you have heard of Einstein and relativity, so why not understand it just a little bit more, what's going on. It won't be a major part of this unit, if you will, but I am going to cover it. I think it's fun. So chapter 6 and 7, part of chapter 10 on projectile motion, and then chapter 35 on special relativity. And then we'll have another exam before we cram more stuff into your brain, right? You look thrilled. All right. You guys have heard of momentum, I'm sure. What do you think it is? How would you define momentum? It's another new concept. Your mom goes, "What are you studying in your physics class?" Momentum. Well, what is that? What would you tell her? You must have some thoughts. All right, non-physics. I haven't taught it to you yet, so just, if you looked it up in the dictionary, what do you think momentum would say? Motion forward. Okay, so there's motion involved, and maybe forward. I'll tell you, it could be backwards. But yeah, it has to do with motion. Yes, good. If you say something has a lot of momentum, that's true. An object can possess momentum. What does that mean? Or give me an example. Get the ball rolling here. That is correct. It factors in mass and motion. So she got the motion part, you got the mass part. So we've talked about both of those. Momentum that we've heard before, it's the product of the two. It's proportional to both. So we define it just like that. There's another equation to guide our thinking. Let me write it up here for you. Momentum. In physics, it's a P. I don't know why. Maybe because M is already taken for mass. But momentum is proportional to mass. It's proportional to velocity. And you know this, whether you realized it or not. Do you want to get plowed over by something heavy? No. Because it has a lot of momentum, that's why. Do you want to get plowed over by something that's moving really fast at you? Probably not, unless you're weird. That's because it has momentum. And if it's really big and moving fast, you're in double trouble. That's momentum. So I like to think of momentum as inertia in motion. It's the simplest way I can sum it up. You remember inertia, I hope by now. Resistance to change, whether you're at rest or already moving. Well, yeah, this makes sense. If you got more mass, you have more inertia, so you resist changing more. So think about it. To get something big moving, well, let's put it this way. Let's see what you think already. This. What's its momentum? Right, it's 0 because it's not moving. But it still has mass and inertia. So to get it moving, it's harder if it has more mass. You have to, in order to give it momentum, the bigger that M, the more momentum you're going to end up having to give it, it's going to be harder. It's harder to move big things. We talked about it with force, but it has to do with that inertia part. Hopefully that's familiar. And the faster you get this moving, well, that's going to take more energy and oomph, if you will, and so it's going to end up with more momentum as well. The reverse is true. Something really heavy has lots of inertia. So in order to stop it, to change its motion, you're going to have to exert a bigger force, right? Because it has more mass, Newton's second law. You're going to change its momentum too. It's got a lot of momentum coming at you because it's big. And so to change its momentum to 0 and stop it, that's going to be a big change. And that's why you don't want to get plowed over by the big football tackler. So which one would you rather get hit by? A big diesel truck going 5 miles an hour, or little Timmy on his tricycle moving at the speed of light? He thinks they're the same? Yeah, I haven't worked out the math, but the idea is they're both bad. Good. The truck, because it has lots of momentum, because it's heavy, but it's moving slowly. And little Timmy doesn't have much mass, inertia, but he's cruising. So both of them have lots of momentum. Inertia in motion. So that's the concept there. There's another concept, and that is impulse. And it's usually an I. If you're going to change something's velocity, what do? Yeah, changing its velocity means it's going to accelerate. Good. And how do you cause that? How do you produce that? Yeah, you apply a force. We've just done that. Well, now we're not just acting on the mass, but we're looking at momentum. In order to change something's momentum, it's still going to affect its motion, isn't it? So we still are going to accelerate it. You're either going to get it moving or try to stop it. It requires a force, just like before. But the key with this is, how long does it take? You can apply a force for a short time or a long time and get different results. And that affects the momentum. So impulse is proportional to how hard you push. Because you push harder, it'll have a bigger effect. But also the amount of time you apply that force. So I guess I never wrote it up here. Momentum is exactly equal to mv. There's no constant of proportionality. It works out exactly. And impulse is exactly equal to the force times time. So those are our equations to guide our thinking and formulas to solve things. Now let's think about what this means. This force is going to cause a change in velocity, a change in motion. It's going to accelerate it. Accelerate what? The mass. Right. But are we going to push at it for a long time or a short time? As we do that, we're going to change the object's momentum. Because momentum is mass times velocity. If you change an object's velocity, you're going to change its momentum. They're kind of tied because they both, see, it's right there. So another way to think of impulse is a change in momentum. If you apply an impulse to an object, you change its momentum. They go hand in hand. If some object's momentum was changed, you know there must have been an impulse. An impulse is a term we don't hear much in the normal world. But in physics, it's just applying the force for a certain amount of time. Any questions at this point? Yeah?
So can you change the impulses from just force or do
Yes, just like the momentum is dependent on either or both. Something big, something fast. Something big and fast. Impulse is affected by how big you push and how long you push it, or both. So yeah, you can get a huge change of momentum, impulse, by applying a really big force for a really long time. Yep?
What are those measured in?
Ah, yes. Ironically, you know how we got the Newton, and in the next chapter you get a cool joule. They give no cool name to this one. So, momentum is mass times velocity. Mass is measured in what standard unit? Kilogram, and velocity? Meters per second. So, momentum is just given in a kilogram meter per second. You write kilogram meter per second. That's its fun, ugly unit. Impulse works the same way. It's a force times a time. Force is in what? Time is in seconds. And so that is just a Newton second. And while we're on it, you remember what force was? It's mass times acceleration. Again, we got a kilogram times a meter per second squared. So this is the same thing as a Newton. So technically, you could substitute this in for the Newton part. And so here's your Newton times a second. I'm going to pause. So this is force. This is a Newton. I just wrote it out in ugly form. Times the time, a second. This one cancels one of these in the denominator. And so that can reduce to just that. And see, it's the same thing. As it should be. Because, I just told you, impulse is a change in momentum. You can think of them as interchangeable. You don't get one without the other. So, if this was how we went the roundabout way to get impulse, it should match momentum. Because if you have a change in momentum, it's going to be in this unit. So, yeah, they're the same thing. Yep? That's this chapter, yeah. Absolutely. Karate chopping, yeah. What is a trained karate person, trying to break a board, what do they try to do? What are they thinking when they're striking? Yeah, they try to go all the way through. Okay, let's pause on that one. How does that fit into this? What would that do? It would. If instead of just kind of that would extend the time of the collision, wouldn't it? That would increase the impulse. and cause a greater change in momentum. That's true. Do they try to go fast or slow? They try to go fast. Okay, that's velocity. So that means they're going to come in with lots of momentum. The board requires so much force to break. And we remember Newton's third law. The force required to break the board, that's what the board needs to feel from your hand. So what's your hand going to feel? Well, equal and opposite. So whatever force it takes to break the board, that's the force your hand has to be able to withstand. And so that's the hard part. Karate choppers train for that. So they want this to be big. They need this to be big to break the board. So if they can have a big impulse, that would make it big. A big change in momentum, and they do that by coming in really fast. Think of it this way, though. I think that was my point. I'm just babbling now. That makes sense? It's a good example. That's in your textbook, too. I think he uses the karate chop as an example, so you can revisit that. Other questions about this at this point? That's the main two concepts of this chapter. We'll conserve momentum next lecture, but I'm not introducing anything new after this. Oh, I like showing you this. It's the the physics math geek in me. All right. Acceleration was equal to what? Meters per second squared. Good. So a change in velocity over time. Meters per second squared. What else did it equal? Distance divided by time. That's velocity. Force over mass. Newton's second law. We could think of it two ways. Whoops. Yeah, you exert a force on a mass that accelerates, which means it changes its velocity. I like that. Exert a force on a mass, it accelerates, which means it changes its velocity. So from Newton's second law here, I'm just going to rearrange this algebraically. We'll cross multiply. If you remember that, you get the mass times the velocity, and that equals the force times the time. And if you don't remember, just multiply both sides by t. They cancel. T goes over there. Multiply both sides by m. The m comes over here and disappears over here. Does this look familiar? What's a change in mass times velocity? Momentum. And what's force times time? Impulse. Yeah, this just falls directly out of Newton's second law. Well, I just told you. You apply a force for a certain amount of time, you get a change in momentum. I think that's cool and simple. So let's do a demo, shall we? My pedagogical marshmallow shooter here. I got cooler looking ones that look like guns that I painted at home. My daughter loves them. My wife hates them because well, as long as we pick up all our marshmallows around the house, she's fine with it. But we don't always do that well enough. So let's see what happens. I need a smaller one. There we go. So they fit. What I'm going to do is I'm going to put one marshmallow in the tube farthest away from you on this end. And I'm going to put the other marshmallow on this end. So there's one here and one here. Then I can put my mouth around it, apply a force equally to both sides. They're about the same mass. So I'm going to apply a force to these masses. What will happen? The one on the end will peter out. This one has bigger impulse? So yeah, impulse is affected. If I'm excuse me, significantly. I'll keep blowing until they're both out. So this one, yeah, has to travel the whole length. Will he feel a force that whole time? As long as I keep blowing, yes. This one, how long will he feel a force? Yeah, until he leaves, which won't be very long. So yeah, the key here is the time. All right, so I'm going to apply the same force to both of them. Look at the formula to guide our thinking over there. Impulse equals force times time. Force is the same, but the time is different between the two. So who will receive the greater impulse? Yeah, the one closest to my mouth. Good. Okay, now what will that mean? If that's receiving the biggest impulse, what's it going to do to its momentum? It'll have a greater change in momentum. Am I changing the mass? No, so what will I be changing? The velocity. Who will have the greatest change in velocity? The one closest to my mouth. So he will exit the tube going faster. Okay, now what will that mean? It'll go farther, because greater velocity covers more distance in the same amount of time. Let's do it, and then I'll walk through that again. So, and it might be hard for you to tell, which comes out of which. So, here is at the far end. And here is at the close end. Doesn't help when I turn around. The camera guy probably doesn't like me either. Yeah. You can really get it up to speed. It's going fast because it had a greater change in momentum, which means it had a greater impulse. How did it get a greater impulse? I applied the same force. I just applied that force for longer. It had more time to accelerate and get up to a higher speed. Yeah. Say that again? Oh, do they exit at the same time? What do you think? What's your gut tell you? He thinks they did. Any other votes? That's all right. I probably don't want it in my mouth anyway. Here it is. Well, let's see. I'll do it again. See if anybody else can tell. I have an idea. I think I know what the answer is, but let's just find out, shall we? That is hard to tell. We need a high-speed camera. I would think the one on the far end, away from my mouth, exits a little sooner. Because as soon as I increase the pressure, the pressure wave travels pretty quickly. And I think it travels faster than the marshmallow does to the end. But that might be fun for me to do a video. Anybody already got a camera you can play in slow-mo? Like my point and shoot, I can record a slow-mo. We'll do it right now. You want to do it? All right, I'll try it with my daughter. She likes using the slow-mo feature on our camera. And then we can watch and see. Or maybe try it out yourself. Come back and tell me what happened. It works with anything. Peas in a straw or whatever. Q-tips in a straw could work. But that's to emphasize, if you apply the same force for a longer time, you get a bigger change in momentum, a bigger impulse. So think of a cannon. How could you make a cannon more effective? Yeah, make it longer. And to a point, that works. I mean, after a while, there's some resistance. But yeah, if you can have that explosion sustained for a longer time, it should come out faster. Yeah. Guns. The bullet can actually come out faster if it's a longer. There's other things involved, obviously. But. All right. Let's do another one. I need 3 volunteers to do this one, or we can't do it. I want to throw an egg into a sheet. Does anybody fancy themselves as a pitcher? Think they can aim? You're not going to be that far. Okay, will you be our thrower? Great, come on down. Now we need 2 holders. We'll have him close so he shouldn't hit you. We need somebody to hold the net. We need another one. Okay, hold this with your right hand and the other corner with your left hand. Okay, thank you. You come over here. We'll put you on that side. You'll hold this with your left hand and the other corner with your right hand. We'll get you an egg. These are real eggs. I won't lie, I forgot to bring a fresh one in today, so they're a little old, but they still break, so you get used to that. So hold your far hand up as high as you can and spread apart so the sheet is a little taut. There you go. Yeah, give him a good wide area. Yeah, and this part's like this. So you're going to chuck it into here, and then the idea with this being it would catch here and not bounce onto the floor. Now, a lot of people aren't prepared for this. Hold tightly. Because he's going to throw as hard as you can. I want you to try to break the egg.
Okay.
Don't miss. Or at least don't hit them. You can miss. Just don't hit them. All right. Okay, there. Is that as hard as you can throw it? You're afraid now, aren't you? It's all right. I got a mop. I can clean up. As hard as you can. Whoa, yeah! All right. That proves our point. Give them a hand. They can sit down now after I grab this egg. Thank you very much. Yeah, that's fun. We'll get it. I'll get it at the end of class here. Yeah. Usually, I've never had one break over there before, so that's good. I've had them bounce off and land on the ground. So yours was like a net. It hit and went off. But see, it's a feature. So we're going to use this. Let's understand the physics. I would venture to say none of you could throw the egg hard enough to break in the sheet. Why? Exactly. It absorbs for a longer time. So we go back to our guide to thinking. This is involved. But probably to make more sense, let's think first what's happening. We got an egg moving. It's got a mass. And it's traveling yay fast. So it has so much momentum coming in to the sheet, correct? What's the sheet going to ultimately do to the egg? Change its momentum to nothing. So the egg's momentum is going to change to 0. So what's the change in momentum? Whatever it was to start with, right? It's essentially going from what it has initially to 0. So the difference is mv. It's going to go from the initial to the final. You with me? So that's also called the what? Impulse. Yeah. An impulse causes that change in momentum. That means the sheet is going to apply that impulse. So it has to apply a force on the egg for a certain amount of time to stop it. Now you said the sheet makes this larger. If this is bigger, what will this do? Yeah, it'll shrink. We have a fixed impulse. It's going to go from whatever momentum it started with to 0. A change in momentum, certain impulse. So that's fixed. So if you make the time of the collision larger, you don't need as much force to stop it. And if that force is smaller, the egg survives. The reverse, the wall. The wall, how does that change in momentum compare to this change in momentum? With the sheet.
It's stopping it very quickly.
That's right. That one's going to happen a lot faster. So how do the change of momentum, the impulses, compare between the two? What?
The same impulse because they're both going to 0, right?
That's my point, but a lot of people don't think. They think that impulse is larger. No, it's not the impulse that's larger. What's larger? It's the force. Good. Because impulses change in momentum. And they're both going to have the same change in momentum. It was going yay fast, some initial momentum, and it ends up at 0, whether it hits the sheet or the wall, it gets stopped. It's just, do you want to do that stopping quickly or slowly? If you do it quickly, this is small and you need a big force, the wall, and the egg couldn't survive that. Or you use the sheet, it takes longer, but you don't need to apply as big a force. And this is practical how? How do we use this every day? To help us feel less forces? Airbags. That's right. That's the point of an airbag. You don't want to hit the hard dashboard or windshield. That's like hitting the wall. Where else do we use it? Pillows. Running shoes, yeah. They're absorbent, right? Now you know what that's doing. It's extending the time of the collision so you need less force for the same impulse. Yeah, I know. You're going to share that with all your friends. Well, you see. But you understand what's going on now. Helmets, pads, high jumping mats, pole vaulting mats, anything that gives a little. Say that again?
A knee or an elbow?
A knee and an... Oh, yeah. Bending. Do you remember Rich doing this? Another instructor goes, yeah, I'll offer an A in the class and $100 for anybody that will jump off of this and land on the ground. And he calls for takers. And before they come up, he says, but you can't bend your knees. Jump off, don't bend your knees. Any takers? Of course not. Why? Because you'll break your leg, exactly. If you land here and you don't bend, you get stopped like that. So, this is small, which means that has to be big to have the same impulse on you and stop you. So yeah, next time you fall, give. Even tuck and roll. Do you hear people do that? You know, you see it in the movies in Hollywood. How many are going to jump out of the moving car or the train? Well, yeah, bend your knees and start rolling, because each of those little joints extends the time of the collision, and it won't hurt as much. It's all about impulse and changing your momentum.
How tight do you think you have to hold the sheet to make the egg break eventually?
Well, I've done that. I've never seen one break yet on the sheet. But when they do it really hard, really tight, that does decrease this. But usually what happens is the egg bounces off too far and then cracks on the ground. But theoretically, if you could get it super tight and stiffer, then it essentially is a wall. And yeah, it would break. Alrighty. Let's do... We often don't think about the time of collision. Things just collide, forces, but because a lot of the times it happens really quickly, and so we miss it. So this is a little splat ball, I call. And if you throw it against the board, it can help emphasize that it really does take a certain amount of time. So if I chuck it, it has mass. That's how I wanted you to throw the egg. It has velocity. So it comes in with momentum. And the board stops it, doesn't it? It changes its momentum because it applied an impulse, a certain force back on this for a certain amount of time. How long was the collision? Well, I don't know, really fast. But enough for it to spread out, come back, and then kick it back. So the spread gives you an idea of the amount of time of the collision. It really did do that, even though we couldn't see it. You guys have probably seen high-speed videos of like hitting baseballs or tennis balls or golf balls, and the ball gets... That's the time of the collision, and that matters. It can have a huge effect in sports. If you throw it slower, it'll come in with less momentum, so there'll be a smaller change of momentum, thus a smaller impulse required, and the time of impact in this case is smaller. Didn't spread out as far. But it didn't need as much force either because the impulse was less. It didn't come in with as much initial momentum. Who doesn't like throwing this at the board anyway? So. All right. Yeah.
Then how come pitchers throw baseballs really fast? One and slow.
How can baseball pitchers throw it really fast?
Why do they throw fast instead of slow?
Oh, why do they throw it fast?
Like I know it's
To make it harder for you to hit. You have less time to react, essentially.
really doesn't go farther.
Yes, very good point.
So like wouldn't it
So, good pitchers pitch really fast, so you're less likely to react and hit it well. However, if you are a good hitter and you can hit a fast pitcher, you can hit it further because of Newton's third law. The ball comes in and hits the bat. So the ball on the bat is the same force as the bat on the ball. And what you're doing is changing the momentum of the ball. So a fast pitch comes in like that. And your bat swings to change its momentum, to stop it. So that'll change it. It'll go to 0, and the change will be mv. But then the bat has to accelerate it back up and shoot it the other way. So there's another impulse going from 0 back up to that speed because it rebounds right off. So it's a similar change, just in the opposite direction. Are you with me? It takes an impulse to stop the ball. It takes another impulse to kick it back out, like the splat ball bouncing off the board. What's the total change? In magnitude, it's 2 mv, ideally. Because you take the final minus the initial, and the minus sign makes a plus. We're going to do this again, so don't fret yet. But it takes mv magnitude to stop it, and mv to turn it back around and kick it out. So the total change, ideally, is 2 mv. And so you can get a huge change in momentum by swinging your bat, and the ball will exit faster, because the pitcher threw it in faster. And you're more likely to hit home runs with a fast pitch. It's definitely a lot harder to hit a home run on a slow pitch.
So ideally you said that it's 2 mv, but does that mean if that's when the batter hits or swings the bat at a certain velocity?
Yeah, the bat speed will affect things also, and I'm ignoring that right now.
So it's just that the batter would just hold that still.
Well, yeah, like a bunt, if he's just holding it out there. Yeah, then it would just be like throwing the ball against the wall, and it would bounce off at the same. So essentially what I did here was as if he could hold the bat perfectly still. But the fact that he's swinging, too, will add to it. And the faster you swing, that'll add also. I'm ignoring that for now for simplicity. And that will affect it, too. The material of the bat, how much it gives, but more importantly, how much energy it can restore. Because some of the energy, which is our next chapter, gets stored in the bat. And then it transfers it back to the ball. And if it doesn't do that efficiently, you lose some of that energy. So yeah, there's a lot of good science in the sports of bats. What's that? Oh, we won't go into that discussion. With steroids, yeah. But you see how the speed is a big factor there to change its momentum. I want to remind you, we said it, but the emphasis that Newton's third law comes into play here too. I showed you how second law came into play to show this relationship. But Newton's third law, when things are in a collision, the forces are the same, right? The force that egg felt was the exact same force the wall felt, right? The wall's bigger, so it didn't break. But the time of the collision was the same too for both. They were both involved in the collision, so the time between the egg and the wall was the same. So if the forces are the same, Newton's third law, and the times are the same, what else is the same? The impulse. But in a collision, when two things hit, the forces are the same, and the time's the same. So the impulse is the same on both objects. That's another key point to this chapter. And it's just a natural result from Newton's third law. The impulses would have to be the same for the same two objects in the same collision. All right, let's ask you some clicker questions. See if you're getting any of this. By the way, somebody left their clicker last time. If you lost your clicker and know your ID number, it's B50645. All right, there's the session ID number in the lower right-hand corner. While you guys are digging out and logging in, next time I'm not really in. We'll discuss conservation of momentum with collisions, and we'll collide all kinds of things next lecture. See how that works. Put some numbers to this too. Everybody logged in that needs to see that number? Okay. Alrighty. Polling's open. Just want to see if you could apply this. Can you figure out the momentum of these two objects and then compare them? How do you find momentum? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 33 people are playing today. All right. 97% the same. The answer is the same. Good. So the first guy's momentum is his mass times his speed. 200 times 10, 2,000. And the second one is still 2,000. Bigger mass, but smaller speed. But the product is still 2,000. So the momentum's the same. It's just to remind you that mass and velocity matter. Okay, go. So double the force and the time of collision. What happens? Think about the effect of each one and then just add the two effects together. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, bang. Okay, most of you think C quadrupled, and you're right. Very good. So impulse is force times time. So if you double the force, you get twice the impulse. But if it takes twice as long, there's twice the impulse also. So both effects double it. So together, you quadruple the effect. Force doubles, time doubles, 4 times the effect. Okay, go. You're in your car, you go out. I've been watching the Bourne Legacy series again and all those car chases. So I'm thinking of him. And he's got to run into a haystack or a wall. The change in the momentum is, how's that compare? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, not as definitive, but most of you thought it was C. And the C's have it. Again, like it says, although the change in momentum is the same for both cases, because they both stop. Whether you get stopped by the sheet or the wall, the haystack or the wall, right? The change in momentum is the same. Do you see that? But do you want to do it quickly or slowly? The one that happens quickly, the wall, is going to require more force. But the momentum change is exactly the same. The impulse required is the same. One more. And go. If you're thinking to yourself, wow, this seems like the last one. Well, good. That means you're getting this. This will be the last question, and then I got a quick little demo, and you're free to go. See how are people doing? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There we go. All right, 91% for B. Good job. That is the same. This is one of my favorite momentum demos because it's simple but straightforward. That's what I want to leave you thinking about. Here's two balls. They're the same size. They're both made out of rubber. They essentially have the same mass. But if I drop them, watch what happens. One of them bounces and one doesn't. So I call this one the happy ball and this one the sad ball. So if I roll them down this, we can try to knock over the block. Which one should I start with? The bouncy ball? All right, so we take it here, we roll it down, boink, it bounces, knocks it over. Do it again, bounces, knocks it over. So, question. What will this one do? Knock it over the same? Knock it over harder? Not knock it over at all? What do you think? This one does not bounce. Your clue is everything we just talked about. It has to do with change in momentum and impulse and forces. There's a collision between the balls and the block. They're essentially the same mass. They roll the same length, so they come in with the same velocity, which means they come in with the same momentum, correct? The block tries to stop both of them. The happy ball seems to knock it over. What will the sad ball do? Still knock it over? More or maybe the same? Same? Less? But it'll still knock it over? Oh, take a guess. Be brave. Okay. Ready? It doesn't knock it over. Why? It comes in with the same momentum, right? Yeah.
The happy ball is shorter time.
That would answer it. If the happy ball was in collision with it for a shorter time, that would answer it. Because less time would mean more force. That's true. Pretty much, though, the collision's about the same time, so something else is going on here. But very good. That's the difference, bounce, and that's the key. So how does that play in? Why does that explain that it knocks it over, the fact that this one bounces? There must be more force because it knocks it over, yes. But why? Why does bouncing mean more force?
Does the bounce transfer more energy to the block?
Essentially, it does transfer more energy, yes.
You could say the block isn't as balanced. It's not very well balanced, so when you hit it, it'll just fall over pretty easily.
Yeah, I did make it so it falls over pretty easily. However, not enough for that one.
But because the bounce ball kicks off it, then
It's that kick. Okay, they come in with the same momentum, right? So to stop them, it requires the same change in momentum, same impulse. Same force, actually. But then what happens? This one gets an additional impulse to push it back up because it bounces. So this one ideally receives twice the total change in momentum, which means it'll feel twice the force. And Newton's third law says, well, this will feel twice the force also, and it falls over. So think about this. When you fall out of a building, your parachute doesn't open, what should you do? Try not to bounce. Go splat. Go limp. I mean, maybe you'll still break every bone in your body, but maybe you're still alive. People that go splat feel less force. That's why drunk drivers often don't get injured as much. They're usually relaxed and limp. And so when they're in a collision with the car, it's more like that than us that, and we tighten up and bounce. So we feel more force. There you go. I'll see you next time.